So far, we've qualitatively understood what friction is and how it impacts a flow through a combustor. It's now time to make that a quantitative understanding, and to do that, we need to start off first by developing a mathematical model for flow with friction. So in friction modeling, what we will be doing is developing a quasi one-dimensional model for this flow with friction, which is also known as Fanno flow. We will aim to express the governing equations as a function of just the Mach number. And finally, once we have that function in terms of the Mach number, we will go ahead and solve it in the next unit and demonstrate that all flow variables can be related to just the Mach number. So without much further ado, let's get started. Consider a gas flow through a pipe of constant diameter d, which has a cross-section area pi d square over 4. The flow enters the domain from the left here and flows along the positive x direction as shown in this sketch. The main aim here is to develop a mathematical model for the influence of friction on this flow. But before we do that, let's look at some other assumptions we need to make in order to develop the model. The first assumption is that the flow is steady. In other words, the mass flow rate through the pipe is constant, which in turn, for a constant area duct, implies that the mass flux m dot double prime, which equals rho times u, is constant. The second assumption we make is that the flow is adiabatic. In other words, the total enthalpy of the fluid is constant. The third assumption we make is that the flow is quasi one-dimensional, that is, all properties vary only along the x direction. We'll also assume that the friction can be modeled in terms of the shear stress tau sub w, which equals the dynamic pressure half rho u square multiplied by the friction coefficient F. In just a short while, we'll be using this definition of the shear stress to write out an expression for the influence of friction on the flow. But before we do that, let's look at some definitions that are also useful, such as the heat capacity at constant pressure Cp, which equals gamma over gamma minus 1 multiplied by R sub g, where gamma is the ratio of specific heats and R sub g is the gas constant. The equation of state can be expressed as P equals rho times Rg times T. The speed of sound A can be expressed as square root of gamma P over rho, which using the equation of state can also be expressed as square root of gamma RT. The Mach number m is the ratio of the local speed of the fluid divided by the local speed of sound A. Once we have these assumptions listed and the definitions written out, we can develop some useful differential form of these equations which we'll use in the development of the mathematical model. In order to do that, let's first take the mass continuity or the mass flux equals constant equation, in which we have rho u equals constant. Let's take a logarithm of this entire equation and then differentiate it to get d rho over rho plus du over u equals 0. Similarly, if we take the equation of state P equals rho RT, take a logarithm of it and differentiate it, we'll get dP over P equals d rho over rho plus dt over t. Now if what I've just said for these two equations is confusing, that is, how do we take the logarithm and differentiate, I would encourage you to pick up the reading that is recommended for this course in terms of the recommended links for ordinary differential equations to catch up with this definition that we've just written here. Continuing, the speed of sound A is expressed as square root of gamma p over rho, and if we square this and then take again a logarithm and differentiate, we'll get dA square over a square equals dP over P minus d rho over rho equals dt over t. Doing the same thing with the definition of Mach number, that is squaring it and then taking a logarithm and differentiating, we'll get dm square over m square equals du square over u square minus dA square over a square. The first term can be further simplified as 2 du over u, and since dA square over a square equals dt over t, we can just substitute for that as dt over t here. Having developed these useful differential equations which we'll be using shortly, let's now return back to the fluid or gas flowing through the pipe. Let's consider a control volume of length dx with the same cross-section area A. We're going to begin by writing the momentum balance for this control volume. As we know from the laws of motion, the momentum balance can be expressed as the total force acting on the control volume should be equal to the rate of change of momentum of the fluid in the control volume. Let's look at what forces are acting on this control volume. On the left hand side cross-section area, we have a pressure P acting on this control volume. We also have fluid entering the control volume with speed u. The force due to this pressure P acting on the control volume here on this cross-section A can be written as P multiplied by A. Because this pressure is acting along the direction of motion of the fluid, we'll adopt a sign convention that makes this a positive force. Likewise, if we look at the exit of this control volume, we now have a new pressure P plus dP, also have a new fluid velocity U plus du. Clearly, we can see that the pressure is now acting again on this cross-section area, but in a direction opposite to that of the fluid flow. Therefore, the force due to this pressure is going to be P plus dP multiplied by A. And because this is an opposing force, we're going to give it a minus sign. The next force, which is what we are really after in this mathematical model, is the frictional force. As we can envision, when the fluid flows through the pipe, at all the contact points where the fluid touches the wall, the fluid is going to try to exert a force on the wall, and the wall is going to resist that force by applying an equal and opposite force on the fluid, which is known as the frictional force. We've just expressed earlier that the shear stress tau sub W is going to be assumed to be equal to half rho u square multiplied by the friction coefficient F. Now if we want to formalize this with the understanding that this frictional shear stress is acting all along the area wherever the fluid touches the wall, which is this circumferential area A sub c, which can be written as pi times d times dx, we can use this information to write a frictional force acting on the control volume as the shear stress, which is half rho u square times F multiplied by the area on which it acts, which is this A sub c, which can be expressed as pi times d times dx. Again, following the same sign convention that we've used all along, we can see that the frictional force is opposing the fluid flow, therefore it gets a minus sign. Looking at this total forces acting on the fluid flow, we can see that the P times A will cancel after we multiply out this expression, the P times A here, and we are left with dP multiplied by A minus half rho u square F times pi times d times dx. That concludes all the forces acting on this control volume. Now let's look at the momentum balance further by looking at the rate of change of momentum. The rate of change of momentum for this control volume can be expressed as the momentum flux exiting the control volume minus momentum flux entering this control volume. Now what is the momentum flux exiting the control volume? The momentum flux is nothing but the mass flow rate m dot multiplied by whatever speed with which the fluid is exiting the control volume. As we know, the mass flux m dot is nothing but the mass flow rate m dot is nothing but mass flux m dot double prime multiplied by the area. Therefore, we can write the momentum flux exiting as the mass flux times area, which gives us the mass flow rate m dot, multiplied by u plus du, which is the speed with which the fluid is exiting the control volume. Similarly, the mass flux entering the control volume is also m dot double prime, and hence the mass flow rate entering the control volume is m dot double prime, which multiplied by area gives the mass flow rate m dot, which multiplied by the speed with which the fluid is entering the control volume u gives us the momentum flux entering this control volume. Therefore, that is the rate of change of momentum of this control volume. again we can see that once we multiply everything on the first term here, this will cancel with this expression, leaving us with m dot double prime a times du. I'm just going to go ahead and substitute for m dot double prime as rho u a du. The next step, of course, is to equate the forces to the rate of change of momentum, and do that as minus dp over a minus half rho u squared multiplied by f by d times dx should be equal to rho u a du. Now I'm going to rearrange terms and also divide by the area A to write this as dp plus rho u du equals minus half rho u square times f times pi d dx divided by cross-section area A, which will be pi d square by 4. Now I've done nothing but move the terms from left to right and rearrange in a way so that I get clean looking terms on the left and I have a slightly messing looking expression on the right, which can be further simplified by cancelling the pi's and the d, and this can be further expressed as minus half rho u square multiplied by 4 f times dx divided by d. I apologize that it ran over the other side, but we'll express this more succinctly in the next line as dp plus rho u du equals minus half rho u square 4f dx over d. Let's box this form of the momentum equation and call it equation 1. Let's just take a second and understand what this momentum balance is telling us. The momentum balance shows that the differential change in pressure plus the change in the momentum equals the force of friction that's acting on the fluid. Let's put aside the momentum balance equation, equation 1 that we just developed, and look at the next assumption, which is the flow is adiabatic. For a constant mass flow rate pipe which has steady flow, the total enthalpy per unit mass and hence the energy balance can be written as Cp times T plus half U square equals constant. You're probably familiar with this expression from the isentropic flow relations. In the next step, let's differentiate this equation and divide it by U square. To write this as Cp times dt divided by U square plus half, differentiating this U square we get 2U du divided by U square. Differentiating the constant we get 0. Let's cancel the 2 with the 2 and the U with this U square. I'm next going to use the definition of Cp, which is gamma over gamma minus 1 times R, and write this as 1 over gamma minus 1 multiplied by gamma times Rg. There's a reason why I'm splitting up the Cp this way, and you'll see why soon, times dt here, plus the remaining terms from here, which is du plus u equals 0. Now if you notice in the differential form equations on the right here, 8 through 11, every single term is expressed as differential of some variable divided by that variable. If you look at this equation here, the du over u fits that format, but the dt does not have a t in the denominator. So let's fulfill that by doing this, and then we can write, since we have to complete the equation we need to multiply by t, let's put that t over here, and I think I missed the u square from the previous line. Let me just finish that here, and we have gamma RT over u square. Okay, so now the dt over t fulfills this format, and we have an interesting expression here, which is gamma times RT divided by u square. As you can see right away, gamma times r times t is nothing but the speed of sound square. So the numerator is speed of sound square, and once we know that, we can see that a square over u square is nothing but 1 over Mach number square. So this entire term in the bracket is going to be 1 over Mach number square. We can use that and further write this equation as 1 over gamma minus 1 times 1 over Mach number square times dt over t plus du over u equals 0. I'm going to rearrange all this and express this as dt over t equals minus gamma minus 1 times m squared multiplied by du over u. Now let me box this equation that we just developed and call this equation 2. In the next part of the derivation, the aim is going to be to develop a relationship between velocity and Mach number for a flow with friction, which is also known as Fanno flow. To do that, I'm going to start by using equation 11, in which we have d of m square over m square equals the last part of this equation, which is equal to 2 times du over u minus dt over t. We said we want to develop a relationship for velocity to Mach number, and the only thing that's stopping us from doing that right away is the fact that we have a dt over t in this equation. But we just developed also equation 2, in which we have dt over t related to du over u. I'm just going to substitute directly for dt over t using equation 2 to get this as dm squared over m square equals 2 du over u minus dt over t, which we said we can substitute for, so let me go ahead and do that right away. So using this equation 2, this is going to be minus of gamma minus 1 times m square times du over u. So in case you're confused about the minus over minus, this is because there was a minus in front of the dt over t to start with, and then dt over t in itself is minus of something, so we just substitute directly. Okay, in the next step, let us simplify this further by first multiplying the minus signs so that we get 2, and then we can of course also pull out the du, which is present in both the terms, to get 2 plus gamma minus 1 times m squared multiplied by du over u by pulling out the du over u. Alright, I'm going to rearrange this to express this as du over u equals 1 over 2 plus gamma minus 1 m square times d of m square over m square, which can also be expressed if I divide this denominator by 2 as 2 times du over u equals 1 over 1 plus gamma minus 1 times m square, divide this by 2, whole thing multiplied by dm square over m square. And there we have it. We now have an equation relating the velocity du over u to the Mach number dm square over m square on the right. This is a very useful expression which will be used further in developing the mathematical model of flow with friction. Therefore, in recognition of its importance, I am going to give it a status of being an important equation to be classified under the differential form and place it over there. Now that we have stored this equation safely, we should also understand that we could derive the velocity Mach number relationship for Fanno flow in this particular form only because of the starting assumption that the flow is adiabatic. Therefore, this equation is not generically true for all compressible flows, and it's important to keep that in mind. Next, let's focus our efforts back on the momentum balance which we have set aside previously. We have two expressions already from working on the energy balance, that is dt over t equals a quantity that's in terms of the Mach number as well as the velocity du over u. Similarly, we also obtained, after some algebraic work, that du over u, or the velocity, is a function of the Mach number related by this equation here. We're going to be using both of these results in furthering the analysis of the momentum balance in order to develop a friction model which is purely expressed in terms of the Mach number m. To do that, let's take the momentum balance equation that we had previously stored away, called equation 1, and divide this by the dynamic pressure half rho u square. As we do that, the first term becomes 2 over rho u square multiplied by dp plus 2 over rho u square multiplied by rho u du equals, since we've divided by half rho u square, this is going to just be minus 4f dx divided by d. Okay, so let's do some obvious cancellations of density with density, the velocity with the u square here. Let's take a look at this expression and try to figure out what we need to do next. As we said before, in the differential form on the right hand side, all variables in all terms have differential of a particular variable divided by that variable, and we aim to reduce our expressions in this form. Clearly, looking at this expression, it's clear that dp is missing the pressure in the denominator for it to be cast in this form. So the first obvious step is to multiply and divide by pressure. Once we do that, we can recognize that we now have dp over p in the same format, and on the second term we have a du over u, which is also in the same format. Let's focus our efforts now on this term that we have grouped here as 2p over rho u square. We want to express this in terms of the Mach number. To do that, we again need to look at algebraically what are the steps that lets us get to the Mach number. First, we can see that there is a p over rho, and looking at the definition of the speed of sound, we can see that square root of gamma p over rho equals speed of sound a, or a square would be gamma p over rho. Since we have a p over rho, the only thing we are missing is gamma, and so I'm going to multiply by gamma and divide by gamma. Now it's conceivable that gamma p over rho is a square, so in the numerator we'll end up having an a square divided by u square. And looking again on the right, we see that u square over a square is Mach number square, therefore a square over u square will be 1 over Mach number square. So taking a big step forward, we can express everything in the parenthesis as 2 times 2 divided by gamma times Mach number square multiplied by dp by p plus 2 times du by u equals minus 4f dx over d. Looks like we made some progress, at least in terms of casting the equations in terms of a differential of a variable over a variable. But we still have pressure, which is not a variable for which we have a direct relationship with Mach number as of yet. In order to move forward, we'll look at equation 9 on the right, which was the differential form of the equation of state, and just simply substitute for dp over p using this equation. When we do so, we'll get, I'm just going to write this on the right here so that we have more space for later, 2 over gamma m square, since we said we're going to substitute for dp over p as d rho over rho plus dt over t plus whatever was remaining here, which was 2 times du over u equals the term on the right, which was minus 4f dx divided by d. Alright, so we took off from taking the pressure and expressing that as density and temperature, but we still haven't gotten to where we need to go, which is express things in terms of the Mach number. But this gets us a step closer to where we want to be. That is, looking at equation 8, we can see that d rho over rho can be expressed in terms of du over u. Similarly, from our work on the energy balance, we have an expression for dt over t in terms of the Mach number and du over u. So the next step is to convert both of these terms, d rho over rho and dt over t, in terms of du over u by simply substituting using equation 8 and equation 2. As we do that, we get 2 over gamma m square multiplied by, using equation 8, minus du over u, where I've substituted for d rho over rho, plus, we're going to substitute for dt over t using this equation here. So that's going to be minus gamma minus 1 times Mach number square multiplied by du over u. All of this is just this first term over here. And of course we have also the 2 du over u, and that equals minus, now let's see if I can write this without making it look messy, 4 f dx divided by d. Okay, that's starting to look a little nicer now, in that everything on the left hand side can be expressed in terms of the Mach number and just du over u in each of these terms. This is where this important equation 12, which was the velocity Mach number relationship that we spent a lot of algebraic time on working out previously, is going to be useful. Clearly we can see that du over u can be expressed as dm square over m square times a factor that's in terms of m square. The next step should be fairly obvious. We're just going to substitute for du over u using this expression. Before we do that, let's pull out 2 times du over u from all of these terms and group them. We get 2 times du over u multiplied by, since we pulled out 2 du over u, the 1 over gamma m square is going to go into the bracket now. So I'm going to get minus 1 over gamma m square, and this will also multiply the second term, minus gamma minus 1. Since we have an m square in the numerator and m square here, they will cancel, giving us gamma. And we also pull the 2 du over u from this expression, so we get a plus 1 equals minus 4 f dx divided by d. Good. We can see from this expression that if we divide this numerator by gamma, we'll get a minus 1 and a minus 1 over gamma. If we get a minus 1 here and we have a plus 1 there, they will cancel. All we have then remaining is the minus 1 over gamma. This simplifies even more nicely as 2 times du over u multiplied by minus 1 over gamma times 1 over m square plus this is going to be minus minus 1. Again, I'll let you figure out how we get from there to here. It's basically very simple algebraic manipulation. Alright, and this should be equal to the right hand side, minus 4f dx over d. Let's cancel the minus signs on both sides so that we can group this and write this whole term after further simplification as, before we do that, let me actually point out that the next step is going to be to substitute 2 times du over u using this term here. And I'll let you work out this last bit of algebra on your own. I'm just going to say, if I substitute for 2 du over u using this and further simplify this term, I can get this expression, which is 1 minus m square divided by 1 plus gamma minus 1 over 2 m square by gamma m square times dm square over m square equals 4f dx divided by d. Let me box this equation. Alright, now let's look at this complicated expression, which is in terms of the Mach number on the left hand side and the friction coefficient F and other geometric parameters on the right hand side. Clearly this doesn't tell us much right away in terms of what is going to be the influence of friction on the Mach number. In the next unit, we'll pick up from this differential equation that we've just finished deriving here and try to see if we can elicit any physical information about what is going to happen to the flow Mach number as friction acts on the flow. From that, we'll proceed to solving this differential equation, getting a final solution which is in terms of the Mach number and the friction factor F. From that, we should be able to then understand fully what is going to happen to the flow Mach number as friction acts on it and quantify the changes in terms of all other physical quantities expressed in terms of the Mach number.